Hello everyone, welcome to the class ECE317. Okay, ECE317. This lecture is for the third week, Monday's class. Okay, last time we have studied the system, right? Type of systems. Type of systems. Okay, firstly let's review something. Type of systems, we have several types. We already discussed the memoryless system. So this is kind of system, the current output value only depending on current input value. Yeah, that's a memoryless system. You don't need to remember anything. Then it is the causal system. Causal system, the output depending on the current and previous output, current and past input, right? Current and past input. So this is a causal system. And then time invariant system. This kind of system, if you shift the input, then the output, it is also shifted by the same way. Okay. And then linear system. Linear system, that is kind of system. If you do some linear operation in the input, then the output will have the same linear operation. Right? Okay. So this is 1, 2, 3, 4, and we have more systems. Okay, stable system. Now we consider stable system. Stable system. The meaning is if a system give a bounded output for any bounded input. Then the system is a stable system. What's the meaning? The meaning is you give bounded input, you will have bounded output, right? Okay. Now let's consider an example to explain it. Actually, we call this the BIBO stable. BIBO stability. Consider example. Okay, we can consider several examples. The first one, consider a system. Suppose the output y of n equal to 3 of x of n minus 1 plus 4 times x squared of n minus 2. Okay, yeah, this one means x of n minus 2 take square. Yeah, we can also write in this way, s squared of minus 2. So we check whether this is stable. Okay, depending on definition, for any bounded input, we will want the output is bounded. So here we can work like this. If x of n is a bounded signal, bounded input, then it is bounded, right? What is bounded? That's the meaning, right? As a word, bounded. Then there exists a number k, so that absolute value of x of n is smaller than k. Okay, this is bounded. The signal now is bounded by k. The value of k is not unique, right? Suppose like you already have a k plus 1 is also a bound, right? Yeah, like a sine of x sine of n. Sine of n, you can use 1 as a bound, maybe equal. You can use 1 as a bound. You can also use 2 as a bound, right? Yeah, so it's not unique, but you have a bound. Suppose x of n is bounded by some k. Then we will check absolute value of y, whether this value is bounded. Okay, what is y? Here we know it is 3 of x n minus 1 plus 4 of x squared of n minus 2. You take absolute value of the whole thing. Then, of course, this will be a value less than or maybe equal to the absolute value of each one. So it's 3 is a positive number, so it is absolute value is still 3. Then x, I replace x by x of n minus 1. N plus 4, here's x of n minus 2. Absolute value, then square. Here's might be smaller because if you have some if x is negative value, you take absolute value, this is positive, right? So this will be smaller. But if all of these are positive, then here will be equal. Okay, then we know x is no more than k, so this is smaller than or equal to 3 times k. And x squared, of course, is no more than k squared. Alright, we get a bound. This is a bound. Is a bound of y. Right? This is a bound of y. Okay, so we found the bound. Then we say x of n is bounded. Bounded. And then we say the system is stable. Alright. Yeah. So if you want to check whether the system is stable, you can just work like this. You choose any signal and suppose this signal is bounded. Use this signal as input. You check whether the output is bounded. Then you can know the system is stable or not. Here's just one thing you have to pay attention. The bounded and stable, these two, they are related but they are different. Right? They're different. The bounded is a concept for a signal. You can consider a signal whether a signal is bounded. And stable is not for a signal, it is for a system. You will consider system as stable. So this is a kind of thing that you have to consider a lot of signal. For any bounded input, you will check whether the output is bounded, right? You need to consider all the signals, a lot of signals. But it is for system, it's stable, right? Stable, okay. Alright, then we can check more. Like y of n equal to n times the sine of n minus 1. Okay, so is this stable? We do the same thing. Suppose x n is bounded by k. X n absolute value is smaller than k, right? Then what is the absolute value of y? We want to find, can we find the y? Now equal to, oh, you can, right? This is n, so it's smaller than n times that k, but n go to infinite. Go to infinite. So you can't have a bounded value, right? For n, the n when n go to larger and larger, the value of y will tend to be larger and larger, and no bound, no number can make it happen, make it always happen. always have the smaller than something. No number, I say some x. I don't I use x, y as a z. Some w. Okay. No number w can make it always have this one smaller than this w. No, you can't do it because you have n go to infinity. So only if x is 0, the n times 0, y is always 0, right? If x is not 0, then the n times it will tend to be larger and larger, or n increase, right? So we cannot make sure input is bounded, output is not bounded. Output is bounded. Actually, now output most possibly it is not bounded. So we say the system is stable, is unstable. Is unstable. All right. Yeah. Okay. So we totally have 5. We have 5 different kind of systems: memberless, causal, time invariant, linear, and stable. Now we consider these 2: linear and time invariant. Okay, we call these LTI system. LTI system, which is linear and at the same time, as well as time invariant. So we have these 2 features. This kind of system, it is both linear and time invariant. Then we have the following. The first one, we say an LTI system can be described as this one. I would say y of n equal to some terms constant ak times x of n minus k. K run from some n1 to n2. Now some term of x, shifted x, and also some bk times shifted y, n minus k, shifted by k. Now k is run from 1 to some m, so at least shifted by 1. Okay. So you can say, what is the output? The output equal to some combine of the input and some previous output. Previous output. Alright, yeah. So you can always write in this way, or you can put them together. This one put this side, and also you can use, suppose you want to use different letter for the coefficient. I write in this way: summation bk times y of n minus k. K run from 0 to that m, and equal to this side is k run from 0 to some n. Is ak x of n minus k. You can write in this way, right? You move all the terms with y to the left side. Then you combine them together. Actually, b0, you can think it is just 1. b0, it is just 1, right? b0, it is just 1. But when you write in this form, actually b0 can be anything, any number, right? So this is more generally. Okay. So an LTI system can always write in this way. You are satisfy equation like this, and we have name for this. We call this as a difference equation. Difference equation. Similar ways differential equation. Differential. How to say differential equation. Similar with differential equation. Differential equation is for continuous time signal. Now it is for discrete time signal. Right. Okay. This is one fact about LTI system. And we can check an example. We'll see y of n minus 1/3 y of n minus 1 equal to x of n minus 1. If I want more, like 1/4 x of n minus 5, for example. This is a LTI system. We have some y term, some x term, and the coefficient before y, they are just some constant. If here you have n, then it is not an LTI system. This is LTI system. Alright. Yeah. You can also write this in term yn equal to x of n minus 1 plus 1/4 of x of n minus 5. Just copy this, and plus 1/3 of y of n minus 1. So this is the previous output, right? Previous output. Yeah, these are input values. Then you can have output. Yeah. Okay, this is the first feature for LTI system. That means we can always write it in this way. And another feature for LTI system, we suppose, okay, this statement is somehow long. Suppose the impulse response of a LTI system is h of n. Then for any input signal x of n, the output signal y of n is the convolution of x, the input, and h, the impulse response. You can write in this way: y equal to x convolution with h of n. This statement is somehow long. Now let's go over it, try to understand it. The first one, suppose the impulse response is something. So what is the impulse response? Alright, impulse response, okay, I will write here. Related concept, I will have several. The first one is the impulse response. The output, this is a signal, right? Impulse response is a signal, actually is output signal. The output of the system when the input is unit impulse delta of n, and usually we denote it as h of n. H of n, and we write in delta of n input, right? Then suppose the system is S, then output side that will be h of n. So it's an impulse response. Okay, this is the first one, impulse response, right? And the second one, we have a convolution, right? we have a convolution. So what is a convolution? Convolution. Convolution of two signals, I say x1 and x2. This one is a signal we usually denote it as x1 convolution with x2. So we use a star for here. In computer, people, in most cases, we use star for times, for multiplication, right? But here, when I write a star for between two signals, we mean the convolution of these two signals. What is this? This is this one. The formula is like this: the summation of x1 of k, not n. Here's n. Now it's k, times x2 of n minus k, and summation for all the k's is this one. So it's a kind of operation, right? You follow the formula. If you know these two, you plug in, you can have the result. So the thing is like, when you know what is the impulse response, when you know what is the input, you can calculate to find y. Use this definition, use this convolution. All right. Yeah. Okay. Then third one. Actually, this is a formula we need to use to prove the convolution result. So we'll see y, the output is xn convolution with h of n. We need to prove it, right? To prove it, we need a kind of formula. We need a formula. Okay. X of n equal to summation of x of k, that of n minus k. K run from negative infinite to positive infinite. You can also write, here I use the notation summation, right? This is summation. You can also write it in terms by term. So we have infinite terms, and suppose I use k equal to -1 as the first term. I give details. So this will be n minus -1, so it'll be +1, right? And x of 0 times dirt of n minus 0, and x of 1 times dirt of n minus 1, and you can have more, x of 2 times dirt of n minus 2, and so on. Right. This way. Here n is the time. N is the time, variable for time, right? Of course, for discrete time case, the n must be integers, 0, 1, 2, 3, 4, right? And k is a kind of index. Index for the summation. Index for the summation. When you do summation, you write in this way, you know how many terms you are used, what kind of term you are used for the summation. Each term is x of k times dirt of n minus k. In each term, k is a fixed number. Not n. N is the time. N could be 0, 1, 2, 3, 4, right? All the time. Here n is all the time, but k just 1k. However, you have a lot of term. You have a lot of term, infinite term. Each term, k is a fixed number. And if you look at all these terms, k will run from negative infinite to positive infinite. But in each term, k is a fixed number. Right? Like here is a k 0. So just x of 0. Right? No changing. But the dirt of n, this n is changing. N is a time. Okay. We need this one. Why can we have these? Okay, let me. I have prepared graph here. So this is suppose this is x of n, and run from negative to positive infinity. Right? We have some values. Then, yeah, for each k, xk is a constant, right, as I told. Then this side, you see, this is delta of n, right? Delta of n. Then delta of n times x of 0. So this is this term, right? And this term, x0 times delta, x0 times delta n. And the next term, x1 times delta n minus 1. So x1 times on this delta n minus 1. N minus 1 is a shift of delta of n minus 1 is a shift of delta of n. So this is a shift signal. Actually, each graph here, it is a signal. For all the time, you have values. All the times you have values, right? For delta, they are zeros only if n is 0. And here you have zeros only when n is 1. You have 1, the impulse at 1. Then when k equal to 2, you have impulse at 2, right? And times x2 is this term, right? This term, this one. All right. Then you do summation. You add all these together. You do summation. Then like see here, when n is 0, it is delta. It is 1 plus 0 plus 0 plus 0 forever 0. So the result will be this one. Right? It is just this term, delta times x of 0. It's just this term. And the second one is delta times x1. So you have this one. Then x2 is this one. And in x3, x4, and so on. In generally, you have this is like this is a n equal to k, and here's a delta of it is x of k, right? X of k, things like this. So actually, this result is same with this, but you look at it in a different way. Here you think different value according to different time. When time is changed, the value of x is changed. And here you think they are summation of some delta, some parts. Each part, the peak value maybe varies, but when you combine them together, that is this one. So here's a combine of parts, part signal. Each part is something looks like this, right? Yeah. Okay. So we have that formula. We can write these in this way. Okay. Then change it better. Okay, now we check the convolution right here. I write that way. Now the output. What is the output of the system? I just plug in. Y of n is the output of the system as when input is x of n. Yeah, this is the meaning of the output. Then, okay, I rewrite x in terms of that formula we just obtained, which is x of k times delta of n minus k. And the k run from negative to positive infinity. Then, we know S is a linear system, right? For linear system, this is summation. I can move summation outside. X of k times delta of n minus k. We have this because linear. Right.
because linear, right? And linear, we use the feature S of some, okay, x1 of n plus x2 of n, or equal to S of x1 of n plus S of x2 of n. Right? So we have these. So here's a lot of terms to do summation inside S. Now you can find S for each term and then do summation. Alright. The next step, summation. I keep the summation, yeah, from here to here. I just copy, yeah. Then S of these. Here we just told x of k, you think is a fixed number, right? So this is a number times a signal, right? You have third of n minus k, so this is a signal. You have n here. Here's n the time, it's changing. So a signal times constant. Then I still use the property of linear. I can move this constant outside, and then S of dirt. This is also because the linear. And the reason is you times constant A on a signal, you use this as input, or equal to, you move A outside the system. This is X of n. Okay. You have this. You have this. Okay. So, okay, we got this one. And then another step, copy the summation from negative infinite to positive infinite. It's a negative infinite. Here's a negative infinite. Then x of k times, we know S, right here, S of dirt. This is the impulse response, right? When you input this dirt, output this H, the impulse response. And also because the time invariant. Because the system is time invariant. So this input is a dirt, shifted dirt, right? It's a shifted dirt, shifted by k. Then output is also shifted impulse response. It's shifted H, shifted by same k. You got it? Yeah. Okay. Now we have this one and then this one. Actually, this is yn equal to x n convolution with h of n. Yeah, you check the definition. The convolution. I have convolution. You see? Convolution x1, x2. You get x1, x2. You have this one, right? This one, yeah. So x1, x2, right? x1, x2, right? This is x1, this is x2, yeah. So we have this one. All right. So we have now we have a formula. This is a very good formula. It's a very good formula. All right. Now we can consider an example. We use a moving average system. Y of n equal to so how many terms for the average? We take 3 terms. Alright. You can also have any terms, 2 terms, 3 terms, 4 terms, 10 terms, or 100 terms. You take average. Right. They are also called moving average. Here's n minus 1 and then n minus 2. So I take average of these 3. Right. If you want more, you plus like x of n minus 3, and here divide by 4. Also moving average, yeah. But okay, now we consider moving average like this. Then this one, this is a LTI system. Is it? Yes, because I said for system, LTI system can be written in this way. Left side you have some y, right side you have some x. It's a summation of terms with x. Here's the summation of some terms with y. Now we have one y and 3 terms with x. And each term, other than x or y, you need some coefficient. The coefficient must be constant, no n, just constant. Now is 1/3, right? These three, all these three, they have 1/3 as a coefficient, right? Constant coefficient. And in y side, you have a coefficient is 1, right? Times 1 in front of it. So this is LTI system. Then, what is the impulse response? Impulse response. So this case input is x equal to dirt. Then what is output? You can calculate it just by calculate one by one. You can list the value of n, then you put the value of x, then you put the value of y. Right? You can do a calculation. So we can start, for example, we start from n equal to -2, -1, then 0, then 1, then 2, then 3, and so on. When n has value like these, what will be value of x? We know x is dirt, right? X is dirt, so this one is 1, and all the rest they are zeros. Okay, this is x. Then what is y? Y is a summation of 3 terms, take average. Summation, okay, like y of 0. Y of 0, you take summation of y of 0, x of 0, x of -1, x of -2. So here's n equal to 0, -1, and -2. You take summation of these 3. Then take average, right? So here's 1/3. 1/3. And if n is -1, if n is -1, right? We have these 3. These 3. Do summation, take average. You have this value. And this one, or this one, they also need 3 values to summation and divide by 3. Now this one is 0, 0, 0 to summation, divide by 3. So it's 0. And similar, when n is -2, you need to do summation of this one and 2 previous ones. All these are zeros. Then take average, still 0. Okay. Now check this. When n is 1, you need to summation of these 3. Take summation of these 3 and then find the average, divide by 3. So this is also 1/3. Right? You need these 3. You need these 3 to summation and then divide by 3. Right? And this is similar. You need this one and this one. You need these 3. So it's 1, 0, 0 to summation is 1 divided by 3. And okay, this one is also summation of these 3. Take average. So what it is? That'll be 0. Right? 0 plus 0 divided by 3. Okay, all the rest, if you want to try more, this is 0, this is also 0. Okay, we have y of n. Actually, this is now this is h of n, the impulse response. This is delta of n, and this is h of n. Right? So we have h of n looks like this, equal to 1/3, 1/3, 1/3, and first 1/3 at n equal to 0. So we have h of n. We have impulse response. If you want to give a graph, it will look like 1/3, 1/3, and 1/3. All the rest are zeros. Right, this is edge of n. This is n. Okay. Alright, impulse response. Impulse response. Now we consider if input x of n, for example, we use u of n as input. This is a step, right? Unit step. Then find output y of n. Actually, we also have a name for this. This is the step response. Step response. The input is a step. Input is step. Response of the step input. So what is this one? Okay, now we know this one must be a convolution of input with impulse response. Right, it's this one. So we need to do some calculation. Okay, so y of n equal to x of n convolution with h of n. Then by definition it will be summation of all the k's x of k times h of n minus k. Okay, now we plug in. For x of k, it is a u of n, right? U of n, unit step. The unit step, it has values 0 or 1. When n is negative, it is 0. When n is positive or 0, it is 1. So here x either 0 or 1. Now for summation, we only need the 1 terms, right? So it's summation for k positive or 0, and then x is 1. X is 1. So it's 1 times h of n minus k. And the k, okay, I write one more line. So this is summation. K will be positive or 0. X is already 1. Then this h. What is h? H, we know we have three non-zero values. 3 non-zero values. They are 1/3. So they are 1/3. 1/3. And here will be n minus k equal to, I write h of n minus k. But n minus k will equal to 0, 1, or 2. We have 2 conditions for the summation. 2 conditions for the summation. Then we write in terms of k. K will be positive or 0. And then this one I write in terms of k. That means k will equal to n minus 1 or n minus 2. Okay? So we have these 3. We have these 3. Let me see. I move k to that side and 0, 1, or 2 to left side. So it's n minus 0, 1, or 2. Yeah. And here's a h of n minus k, which must be value 1/3. 1/3. Then how many terms do we have? That depending on n. Depending on n. We want k is positive, and also we need to consider like this is n, this is n, this is n minus 1, this is n minus 2, and I also want k larger than 0, or maybe here, or maybe here, or maybe here. We have 4 cases, right? Other k large, maybe you contain these 3. Maybe k large you only have larger than 0. You only need you have these 2. Or k large you have just 1. And even if you want k is larger than 0, then all of these three, they are negative. All of these three, they are negative, right? So actually we have 4 cases. 4 cases. This case, k is here. K is larger than 0, so 0 is here. That means n minus 2 larger than 0. Then this is a 3 of 1/3, and n minus 2 larger than 0, right? N minus 2 is in the side k larger than 0, k larger than 0. And the second here, for these, you have 2, so 2 of 1/3, 2 of 1/3, and this is case n minus 1 larger than 0, right? And this one is the case n larger than 0. Now here's 0, n larger than 0. This is a 1 of 1/3. Okay, the last one, the n is smaller than 0. This is just nothing, right? Okay, then I write one more details. This is 1, 2/3, 1/3, or 0. Here's n larger than 2, right? N larger than 2. This is n larger than 1, but cannot be 2. 2 is here where I use, so this is just n equal to 1, right? N equal to 1. And this is also same. I want n larger than 0, but larger than 2 and equal to 1 I already used, so this is just 0. And the last n smaller than 0. Okay, so we have the output. Output is this one. We can give a graph to see how it looks like. It's a 0 for negative n, they are zeros, and when n is 0, it is 1/3. When n is 1, it's 2/3. And when n is larger than 2, it is 1, right? All n is larger than 2, the value is 1, like this. So this is like, it's still things like that. It is also kind of step, but it is not just one step from 0 to 1. It is separated by 1/3, then 2/3, then 1. Input is a unit step. It will go up to 1, right? Input, this is output, and input is just one step, right? From 0, then jump to 1, then keep 1. This also from 0, then jump to 1, but this jump, it is span two step, right? 3 step, 0 to 1/3, then to 2/3, then to 1. Alright. Yeah, this is input, this is output. Okay, so we can always work like this. When you have a system, you want to find the output, then firstly you try to find the impulse response. The impulse response, like here, like this example, we can just find the impulse response by a list of the values. You can just list all the values, try to solve it. Because input is quite simple. Input is this kind of thing, right? It's dirt. So you can do this very easy. Yeah. And then for some other kind of given input, this is like now x is a unit step, then you follow the formula input convolution with the impulse response, you can find the output. Alright. Any problem? No. Yeah, if you have problem, you can leave your problem in the piazza or go to the office hour. Our office hour and my office hour is on Wednesday, 4 to 5 p.m. And we have 3 TAs in this course. They also have office hour. You go to Blackboard, you go to Syllabus, you can find the information of the office hours of TAs and mine. Yeah. Alright, that's all for today. See you next time. Bye bye.